we were able to calculate some limits at infinity for very simple functions by just thinking about the general trend of what happens when x gets very large, if we're going out to plus infinity. But for all but the simplest functions, that actually isn't going to be a very good trick to use, just because our intuition will usually fail us because we don't understand infinity very well. So for example, think about calculating the limit as x goes to infinity of this rational function, 4x squared minus 3x over 3x squared plus 7. So you might just think, well, the numerator is a quadratic that opens upwards because it has a positive leading coefficient. And so the numerator, as x goes to infinity, the numerator is going to go to plus infinity. And the denominator is also a quadratic that opens upwards, and so as x goes to infinity, it will also go to plus infinity. And now we have infinity over infinity. Well, what does infinity over infinity mean? Unfortunately, infinity over infinity doesn't really mean anything. It's undefined. And that's because what infinity over infinity ought to mean really depends on the context that this infinity over infinity came from. It's tempting to say, well, since it's infinity over infinity, shouldn't it be equal to 1? But we'll see that that's not actually the case. It's not usually the case. So when you see infinity over infinity, you have to remind yourself that infinity over infinity just means try harder. It's just like 0 over 0 doesn't mean 0, it means try harder. Okay, so what do I mean by try harder? Well, what that means is usually there's going to be some sort of algebra trick that we can do to sort of tame the infinities and understand what's really going on here. And in this situation, right, the reason that this turned out to be difficult was because of the fact that any polynomial goes to either plus or minus infinity as x goes to infinity. So what we need to do is somehow tame the polynomial. We need to make its degree not positive, right? Any positive degree polynomial is going to fly off to infinity when x gets big. So what we can do is, see the highest degree term in the numerator and denominator is 2, so we can multiply the numerator and denominator by 1 over that power of x. So multiply the numerator and denominator by 1 over x squared. And this is an okay thing to do because, when I say it's an okay thing to do, what I mean is it's an algebraically valid thing to do because this ratio it's 1 as long as x isn't 0, but x is going to infinity, so x isn't 0. We're definitely a long way from 0. So I'm just multiplying this rational function by 1, but I'm writing 1 in a very weird way. So if we now distribute through the numerator and denominator, we get the limit as x goes to infinity of, so in the numerator, it's 4x squared times 1 over x, and that's 4, minus, and then 3x times 1 over x squared, that's 3 over x, over, now in the denominator, we need to distribute this 1 over x squared, so 3x squared times 1 over x squared, that's 3, plus 7 times 1 over x squared, that's 7 over x squared. Now it might look at first like things are worse than they used to be, just because this function sort of looks worse. It looks like it's less simple than it used to be. But something interesting has happened. Now if we think about the general trend as x heads towards infinity, so 4, as x goes to infinity, what happens to 4? Well, it stays 4. Right? 4 doesn't care what x does, it's always just 4. Okay, now minus, and now let's think about 3 over x. What happens to 3 over x as x goes to infinity? Well, 3 over x, remember, since x is going to positive infinity, we should think of this as 3 over some unbelievably huge number and getting huger. What happens to a fraction whose numerator is 3 and whose denominator just grows forever? Well, that's going to go to 0. Right? The bigger the denominator, the smaller the fraction, but the denominator is growing without bound, going towards infinity. And so this fraction is going to get smaller without bound towards 0. And in the limit, of course, you get 0. All right, so now let's look at the denominator. Well, in the denominator, the same kind of thing happens. What happens to 3? It's just 3 plus what happens to 7 over x squared as x goes to infinity? Well, 7 over something growing without bound goes to 0. So we get 4/3. The value of this limit is 4/3. Notice that it's not 1, it's 4/3. So, this sort of tempting canceling the infinities to get 1 definitely does not work. So, right, don't do that. All right, so if we looked at a graph of this function, what we would see is that there's a horizontal asymptote at 4/3. All right, for another example, let's look at this one. So as limit as x goes to minus infinity of x minus 1 over x squared plus 7x minus 3. So again, if we just plug in infinity, so to speak, I put air quotes around that, we're going to get minus infinity over plus infinity. And again, sort of the wrong way to think about it is, well, let's cancel these infinities and we get minus 1. That doesn't work. Right? Infinity over infinity just means we need to try some other algebraic trick. And for this one, well, the numerator has degree 1 and the denominator has degree 2. So why don't we use that same trick where we multiply the numerator and denominator by 1 over some power of x. But it's a little unclear what power of x we should choose. Should we choose should we choose x to the first power, or should we choose x to the second power? I think either would actually work in this case. Let's do x to the second power, I guess. If one didn't work, we could just try the other one. Okay, so let's distribute this through the numerator and denominator. So limit as x goes to minus infinity of, let's see, x times 1 over x squared is 1 over x, minus, and then 1 times 1 over x squared is 1 over x squared, over, and then in the denominator, x squared times 1 over x squared is 1, and then plus 7 over x minus 3 over x squared. All right, and now we can ask ourselves, what happens when x gets really big? Well, when x gets really big, this 1 over x term, that goes to 0. Notice that this 1 over x term goes to 0 even though x is going to minus infinity and not plus infinity. Right? It doesn't matter whether the denominator is getting to be a huge positive number or a huge negative number. In either case, this fraction is headed towards 0. Same thing for 1 over x squared. This heads towards 0. 7 over x also heads towards 0. And 3 over x squared also heads towards 0. So what we end up with is, in the limit, we get 0 over 1. Well, that's 0. So this rational function actually has a horizontal asymptote at y equals 0. All right, for a final example, let's look at this one. Limit as x goes to infinity of x cubed minus 2x squared plus 7 over 4x minus 2. All right, well, again, if you just plug in infinity, you get infinity over infinity, which just means you should try something else. Well, this trick with 1 over x really seems to be doing the job, so let's try it again. And it seems like we should maybe use x to the first power because the degree in the denominator is 1, or maybe we should use x cubed because the degree in the numerator is cubed. And it's not totally clear which one is the right approach, but let's try just using the degree of the denominator and see if it works. So when we multiply this out, we get the limit as x goes to infinity of, so distributing through the numerator, we get x squared minus 2x plus 7 over x over 4 minus 2 over x. Now we have to ask ourselves what happens when x gets big. All right, so this 2 over x's part is going to go to 0. 4 is going to stay 4. 7 over x, that's going to get very small. But now we have to ask ourselves what happens to this piece, x squared minus 2x. One thing we can't do is just plug in infinity, because then we would get infinity minus infinity. But what's infinity minus infinity? That doesn't really mean anything. It's tempting to say maybe it's 0, but we'll see that that's not the case. It is in some cases, but not in this case. So x squared minus 2x. Well, when x gets really big, right, we can look at this as just a polynomial. It's a quadratic, right? And when x is really big, only the leading term of the quadratic matters, right? When x is really big, we're asking about the behavior of a parabola that's opening upwards far to the right. But a parabola opening upwards far to the right, it's going up to positive infinity. So this part's going to positive infinity. So what we're getting here is infinity in the numerator, 4 in the denominator. That's definitely positive infinity. So this limit is positive infinity. You can see that in all of these three cases, although we got very different results, positive infinity in this case, 0 in our second example, and some non-zero finite constant in the first example, the trick we used was actually the same. Right? We just multiplied the numerator and denominator by some power of x. We had to be a little careful choosing which power of x, but 1 over some power of x in the numerator and denominator somehow tamed the infinities and gave us values for our limits.